All right, welcome everyone. This is our 33rd online Spintronics seminar. I am Kirill Belchenko from University of Nebraska. Our speaker today is Professor Iris Ferreira from the University of York. His talk will be about interfacial spin-orbit torques in the atomically thin limit. Dr. Ferreira obtained his PhD in physics from the University of Porto in Portugal in 2009. And the topic of his research was quantum entanglement in macroscopic systems with collaborative work performed at the ICOKI in Vienna. That's the Institute of Quantum Optics and Quantum Information. After that, he worked as a research fellow in condensed matter theory at the University of Minho in Portugal, and then at the Graphene Research Center at the National University of Singapore. In 2014, he was awarded a university research fellowship by the by the Royal Society, and he now leads a research group at the University of York, where he's currently an associate professor in the Department of Physics. His research focuses on the development of many-body theoretical methodologies to understand quantum criticality and emergent spin-orbit coupling phenomena in low-dimensional systems. Dr. Ferreira is a co-founder of the open source KITE initiative for quantum transport simulations with billions of atoms. From 2015, he is also a member of the EPSRC's Peer Review College. So with this, I will turn it over to Iris, and he'll tell us about these intriguing interfacial spin-orbit torques in the atomically thin limit. Please, Iris, go ahead.
Thank you for the introduction. I'd like to start my talk by mentioning the important role that this online Spintronics series has been having amid this awful pandemic we are living through. So it's been an excellent forum for getting updated about latest developments in Spintronics and also to get some new ideas for research. So I'm very thankful to the organizers, my colleagues Kirill Belchenko and Shinfan, for putting this together, and thank you very much for inviting me today. So as mentioned, this talk will be about interfacial spin-orbit torques in the atomically thin limit. So the aim of this project was to develop a microscopic theory that could make some predictions about the origin and the magnitude of spin-orbit torques generated by two-dimensional materials. So I'd like to start by the most important slide in this talk, which clearly is about the young researchers in the group that lead their own research projects. With respect to today's talk, I'd like to particularly mention Frederico Souza, who's the first author of the study I'm going to report today. He's done an excellent work at computing diagrams. So it's been a very exciting project, and I'm very thankful for Federico for this huge effort amid this pandemic again. So this was a really difficult time, but the project was successful. So we believe we now have a good understanding of the spin-orbit torque at this type of interfaces. I would like to also mention my collaborators over the years, over the last few years that on Spintronics, both on the theory and the experimental side. I'd like to particularly mention the experimental groups led by Sung-Jae Cho and Stuart Cabell, who played a role recently in demonstrating reversible Rasch-Weldestein effect in two-dimensional electrostructures. So with whom I had the pleasure to collaborate. I'd like to also mention Mirko Militari. He's no longer with us, so he left for the private sector, I'm afraid, but he did an excellent job at developing diagrammatic techniques so that we could understand spin-orbit coupling phenomena in systems where low energy quasi-particles are basically Dirac fermions. So that requires a slight adjustment of the way we do the things. I'll explain this later in the talk. I'll also like to mention my recent theory collaborators, Anderson Barbosa from FRP in Brazil, João Vena Lopes, who is the main developer of KITE, is from the University of Porto in Portugal, Branislav Nikolic from Delaware, and Jen Tatara from Riken, Japan, with whom we collaborated on this project. So this is an outline of the talk today. There's going to be an introduction. Then I'll go on to 2D layered materials. Here there'll be a little bit of an introduction again as to why these systems are attracting interest from the Spintronics community. And then I will mention the key role played by both pseudo-spin entanglement in these systems and the skew scattering. And finally, I will mention what is my view on the importance of skew scattering for other Spinobit torque devices. Basically, I'm thinking of metallic bilayers and topological insulator-based systems. So Spinobit coupling is one of the most fundamental interactions in condensed matter physics. Its non-relativistic limit is well known, so I'm writing here in the slide. So the presence of the velocity of light makes it clear this is a relativistic effect. One could be tempted to think that this Spinobit coupling would manifest only in the presence of very heavy elements. And that's not actually the case, because the Spinobit matrix elements grow very quickly with atomic number, because the more electrons you have, the stronger the field is going to be, and also the more electron spin moments you have to experience that field. So the Spinobit interaction, in fact, plays an important role even in systems with intermediate Z number. So that's the reason why in condensed matter physics we've been studying this Spinobit interaction from various perspectives. In a crystalline environment, there is no rotational invariance. So in fact, the best way to think about the Spinobit coupling is an effective field that couples the spin electron degree of freedom S with a pseudo-magnetic field B, which depends explicitly on the momentum of the quasi-particle. So this is a very general description of Spinobit interaction that highlights this interplay of orbital and spin degrees of freedom. So the Spinobit coupling has taken center stage in recent years in many topics. So it's been quite exciting. So here I'm mentioning the example of Z2 topological insulators as realized in mercurium telluride quantum wells. So it's well known and well understood that Spinobit interaction is the basic ingredient behind the band inversion mechanism that drives the system into this quantum phase transition towards a quantum spin insulating phase with topological protected edge states. So these edge states are special in the sense that are spin polarized and they are protected against elastic backscattering. Another example is found in low-dimensional systems where Spinobit coupling is the driving force behind the plethora of spin and anomalous Hall effects displayed by this type of systems. And also like to mention more recently the role of spin-orbit coupling in optics, in particular experiments performed with atomically thin semiconductors, such as group 6 dechalcogenides. Here there's an example of a molybdenum disulfide, and you see this circularly polarized light that couples in a selective way to the momentum of quasi-particles, so to the K prime points in the band structure. So this spin valley selection rule is a result of both the strong Spinobit interaction in this system and the lack of inversion symmetry. So this can be seen in photoluminescence spectra. So in fact, one can prepare superpositions of right and left circularly polarized light and observe spin valley coherence. It's a quite exciting development in recent years. And researchers in the field actually have taken this further, and they have recently embedded transition metal dechalcogenides in optical cavities in order to achieve strong coupling between photons and excitons. So it's a quite exciting time to be looking at Spinobit coupling effects. So today in my talk, I'll be focusing on interfaces, and we know that interfaces are special because they lack inversion symmetry. So mirror symmetry is broken at an interface between two materials, and that leads typically to a fast variation of electrostatic potential. In other words, we have typically strong electric fields at the interface, and that is good news for us because that means we can effectively couple the momentum and spin degrees of freedom via the so-called Rashba interaction. So that is written here in the middle. So this is actually a quite general way of writing the Spinobit or the Rashba Spinobit coupling. So there's alpha SO here is a coupling constant that parameterizes the strength, and P cross C comes simply from the symmetry of the Spinobit coupling of this system. These type of effects can also be found in bulk. Actually, in this graph, you can see beautiful ARPES data from Christian Ast and co-workers, where they looked at metallic alloys, and they can see perfectly the appearance of the spin split bands that we associate typically with the Rashba effect. So this is some sort of bulk Rashba effect that takes place because inversion symmetry is broken at the level of the unit cell itself. So it's several ways of enhancing this type of effect. So it's quite interesting. So I'd like to focus today on, particularly on anti-damping Spinobit torque at ultrafine interfaces. And there are two basic models to understand what might be the origin of anti-damping and field-like Spinobit torques. So what I call here model one is based on the Spinov effect. So if you look at the schematic on the right from the nice review by Manchon and co-workers, you see a ferromagnet on top coupled to a normal metal below, and GE is the current that is applied to the normal metal. And via spinol effect, a spinol current is produced, and this spinol current transfers angular momenta to the ferromagnet, which drives the magnetization dynamics. So this is the bulk mechanism, and it's actually a very efficient way of inducing anti-damping Spinobit torque at the interface. There's another model, which is commonly referred to as the interfacial mechanism. And this one is based on inverse spin galvanic effect, which is also known as the Edelstein effect. In this effect, a current is applied to the system, and suddenly or spontaneously, your electron gas is magnetized. And the magnetization of the electron gas, the spin polarization of the charge carriers, is orthogonal to the applied charge current. You can also see this in the nice schematic. And this can also induce Spinobit torques. And in the ultrafine limit, according to scattering models and phenomenological models, it is believed that this torque is mostly field-like. So this is the basic spinol effect, inverse spin galvanic effect dichotomy, which is conceptually simple, but it does not capture the full spectrum of Spinobit torque mechanisms, as it's been becoming more and more clear. So atomically thin materials are actually quite interesting because they are very simple, at least from the theoretical perspective from my side, which means that we can actually use them as a platform or a testbed, if you like, to explore the origin of such interfacial Spinobit torques. So we have a relatively simple class of systems that we can investigate in detail and determine what are at least the predictions from the theoretical side. Okay, so let's now move to the next part of the talk. So here I would like just put everybody on the same page and explain what is the origin of all the excitement in graphene-based spintronics, which is a field that basically emerged in 2006 with the first experiments demonstrating spin injection in graphene by the Groningen group led by Bart van Vis. So more recently, there's been a revival of interest in graphene spintronics, and the reason is because experimental groups found ways to enhance the extremely small Spinobit coupling of graphene. So one way is to use chemical functionalization. Unfortunately, that procedure that involves decoration of graphene with other atoms and molecules is not very easy reproducible. So another strategy that is perhaps more successful is to integrate graphene with other two-dimensional materials. So this is so-called the van-der-Waals heterostructures. So in this case, we still have the nice electronic properties of graphene, or the basic electronic properties preserved, because the interaction is, van der Waals interaction is weak, but it's sufficiently strong so that you can actually enhance by 100 or even 1,000 times the Spinobit coupling of graphene, so that actually it has observable consequences. So one of those consequences is the modification of the spin dynamics. So as demonstrated by the group of Sergio Valenzuela a few years ago, the spin dynamics of graphene, of pristine graphene, is absolutely isotropic. So there's, whatever is the limiting factor is such that the spin dynamics does not distinguish out of plane and in plane directions. But the situation is completely different once we interface graphene with the transition metal dichalcogenide. And this is because of the interplay of proximity-induced Spinobit coupling and intervalley scattering that leads to this huge enhancement of the ratio of out of plane and in plane spin lifetimes. So this is an example of the consequences of proximity-induced Spinobit coupling on a system such as graphene. But there is more. So if we look carefully, and a number of theoretical groups have been focused on this, including ourselves, there's actually the possibility to induce a variety of Spinobit coupling phenomena, non-equilibrium phenomena in these systems. And the reason, as I'm going to explain in the next few slides, has to do with the rich interplay of spin and pseudo-spin degrees of freedom. So a series of works have theoretical predicted that spinol effect and the inverse spin galvanic effect in these systems not only should be observable at room temperature, but can be efficiently tuned with the gate voltage by changing the carrier density of your 2D material-based device. But also you could observe new effects. One such new effect that we are quite excited about it, it's the all electrical spin switching effect predicted by Ofidani and coworkers back in 2017. So in this effect, basically, what happens is that the non-equilibrium spin polarization induced once a current is applied to the system, this spin polarization vector can be controlled with the backgate voltage. So basically, the sign of the polarization depends on the polarity of the charge carriers. And that's in contrast to topological insulators, where this sign is always fixed. So this was demonstrated by Songjai Shou in collaboration with us recently. And also it has been demonstrated the reverse effect, so the spin galvanic effect. So that's quite interesting that in the same experimental setup, we can change the gate voltage. So changing the Fermi energy, which changes all the transport coefficients of the system. At the same time, we can probe charge to spin and spin to charge conversion. Another very interesting development led by the groups of Casanova and Sergio Valenzuela in Spain, and also by the group of Van Wies in Groningen, relates to this rich interplay between different phenomena in these systems. And in this case, the inverse spinol effect and the spin galvanic effect. So particularly in the work of Benitez, they were able to extract very accurately the dependence of the transport coefficients associated with spinol effect and spin galvanic effect as a function of the Fermi energy of gate voltage. And it's quite striking that these dependencies matches qualitatively and quantitatively what is predicted by the theory. So that's quite exciting, and that highlights a rich interplay of intrinsic and extrinsic effects in these systems. So what is the reason behind all of these effects that suddenly appear? Well, the reason is the pseudo-spin coupling. So if we look carefully at the crystal structure, if we start with the simplest possible monolayer, and that would be graphene, we have clearly an internal pseudospin, which is the sublattice, because this is an Otta-Bravais lattice. So we have two interpenetrating triangular lattices. So when we have to write down or think about wave functions in this system, we have to deal with the A and B sublattices. So this forms an SU2 internal space, which is tantamount to the electron spin. Now, when we look at the Spinobit coupling, suddenly things become very interesting. And the reason is that these sublattice and spin, they have to be taken at the same on equal footing. So if we write the total angular momentum operator Jz, we immediately see that these two spin operators appear together. And that means that Spinobit coupling in these systems is not so much an interplay between spin and the momentum directly, but it's an interplay between the spin and pseudo-spin degrees of freedom. So it's two qubits talking to each other. So that's quite interesting. And if we think about simply, again, the graphene example and apply symmetry, so if we use the point group symmetry of the honeycomb layer, which is D6H, we see that the only possible Spinobit interaction is the famous Ken-Meillet interaction, which is responsible for the appearance of a Z2 quantum spinor phase in the system, which couples precisely the pseudo-spin and spin degrees of freedom. So this is quite general, and in more complicated heterostructures in the presence of interfaces, what will happen is that now these degrees of freedom will be mutually coupled by Spinobit coupling. So we can start by taking graphene and proximatize it, for example, with a transition method with chalcogenide, and thereby inducing spin valley coupling. And that brings down D6H to D3H. And we can go further and realize this in such a way that the interface is atomically sharp, so that you expect a sizable Rashbe effect. And when you do so, you break the symmetry down to C3V. Of course, we can also do this with transition metal dechalcogenides by, again, taking an interface to another system. And when this is coupled now to a ferromagnet, because we'll be interested in magnetization dynamics eventually, then things become even more interesting because we break the C3V symmetry down to C2V or even lower. So the interfacial breaking of inversion symmetry, in other words, the Bishkov-Rashbe effect, then gives rise naturally to entanglement between these two special spin degrees of freedom. So if we write down the block wave function for around, let's say, one of the K points, we see that there's no way around this. We have to take all the possible combinations of sublattice A and B and spin up and down. So generally speaking, broadly speaking, these states will be entangled. In other words, we cannot recast this expression into a product of so-called separable states living on different subspaces. So these states will tend to be highly entangled. So what are the consequences? So to understand the consequences, we have to think about a particular case first. So let's consider a transition method dechalcogenide graphene ferromagnet. And this graph highlights the bond structure of states that are basically graphene states that will be inside the huge gap of the transition metal dechalcogenide and will be perturbed both by the transition metal dechalcogenide and by the ferromagnet. So we're going to have the spin splitting of these states as a consequence of proximity-induced spin valley coupling, Rashbe effect, and proximity-induced magnetic exchange coupling from the ferromagnet. So the bond structure then develops this interesting Mexican hat region at low energy. So if you look at the lowest conduction energies, you see these Mexican hat, which hints at a very fast dependence of the spin texture with momentum. And actually, if you care and evaluate the spin texture, you'll see that it evolves very quickly. So it's non-coplanar, even in the absence of exchange coupling. So that's quite remarkable. And it's the interplay of Rashbe effect and spin valley coupling. So now we can look at what happens at close to the Fermi level. So let's say that we have electron doped sample with Fermi energy around 0.1 electron volt. It's a typical Fermi energy for one of the systems. So let's look what happens around this, where the action will take place. So we can start by looking simply first, before the actual transport problem, the actual non-equilibrium problem, we can look at the equilibrium density matrix of the system. So we can look at what kind of correlations already exist in the absence of an applied current. And this actually, it's quite interesting. So if we use our intuition, we know that in the inverse spin galvanic effect, there is a perfect locking of spin and momentum. For example, in a two-dimensional electron gas or in a two-polarized insulator, if you like. And that means that basically that we have maximal entanglement. So you can see degree of entanglement in K space as a sort of witness, or better, figure of merit for the current-induced Spinovi torque capacity of your system. So these correlations that exist in equilibrium, once you apply a current somehow, will pass onto the non-equilibrium state. So they will already say something about the capacity of the system for inducing Spinovi torque. So let's try and compute the entanglement for this band structure. And this is what happens. Several interesting things happen. So to compute entanglement, first we need an entanglement measure. And in this case, there is an entanglement, there is such an entanglement measure, it's called logarithmic negativity. So this is because the problem is effectively a problem of 2 qubits. So we can construct a proper entanglement measure that does not increase under local operations and classical communication. So in quantum information theory, that's called a proper entanglement measure. So we're quite lucky we can do that for this example and compute the actual entanglement as function of the Fermi wave vector or energy, if you like. And what you see is, you see many interesting things. You see first that the entanglement tends to decrease as you increase the Fermi wave vector. That's a general tendency for these systems. And you also see a very fast variation close to the direct point. And this again links to the Mexican hat behavior I discussed before. And you also see that anisotropy plays a big role. So if by choosing different directions in momentum space, so the blue and dashed lines represent orthogonal directions in momentum space, let's say X and Y directions, around the K point, you see this huge anisotropy that is induced by the magnetic exchange coupling. So in this particular example, the magnetization was taken at 45 degrees, just not to have any perfect direction for the calculation. Of course, if we want to get serious about this, we need to compute actual transport coefficients. And there are several ways of doing this. But first, we need a unified description for these two-dimensional van-der-Waals heterostructures. And to do this, we use a field theoretically inspired approach. So basically, we like a construction that we can apply to any the heterostructures of monolayers, or virtually any heterostructure of monolayers. And to do that, what we need is the right set of gauge fields. So by coupling these gauge fields to the momentum via minimal coupling, we can generate all the couplings, if you like, in the theory that will describe the actual experimental scenario. So there are two important ingredients here. There is the spin-orbit and exchange coupling, which is a non-abelian gauge field because these vectors actually have actually an internal structure, so they are matrices. And there is the orbital component, which plays an important role in two-dimensional materials because we know in transition methodic chalcogenides, A and B sublattices are equivalent, and there is a huge staggered on-site energy that opens a gap. So this has to be included in the theory if the aim is to have a unified description. And here inside these blue and green boxes, you see the actual expressions for the gauge field. So the Spinobit coupling are ready for C3V symmetric monolayers is quite rich. So you have the Rashba coupling, that's because of broken mirror symmetry around the plane, but you have Ken-Melley interaction, but also spin valley coupling. The spin valley coupling, you see, it's quite interesting because it couples to the time component of the pseudo-spin operator. In other words, it does not depend on the pseudo-spin operator at all. The exchange coupling and the orbital terms are written inside the green box. And in the theory, I like to have the freedom to have the magnetization pointing in any direction because that will play an important role in the angle dependence of the Spinobit torque. And the parameterization of all these couplings can be performed using first principles calculations at different levels and also by Slater-Coster approach. And of course, we can also should also take experiments as guidelines, but we have a good understanding that these couplings for graphene should be on the order of 1 milli-electron volt, and for transition metal of chalcogenides can be 1 or 2 orders of magnitude larger. So there are two typical scenarios that we have in mind in this talk. So one concerns what I'll be calling the weak proximity effect case, which is a graphene-based heterostructure like graphene on transition metal of chalcogenide, that will be coupled to a ferromagnet. And this ferromagnet can be typical thin film ferromagnet, but could also be a two-dimensional material-based ferromagnet with perpendicular magnetic anisotropy. And the other scenario will be of a sleek-conducting transition metal of chalcogenide coupled directly to a ferromagnet thin film. So this leads to, of course, vastly different band structures. So in the weak proximity effect case, we have the band structure on the left, in which we have, again, this Mexican hat, typically this Mexican hat region, and then we have linear dispersion that resembles the Dirac cones at high energies. On the right-hand side, you see the typical band structure of a transition metal chalcogenide, which experiences some magnetic exchange coupling due to proximity to the ferromagnet. So you can see some signs of the anisotropy, again, solid and dashed lines refer to energy versus K curves along different directions in momentum space. Intuition can also help, and we always start by looking at the equilibrium spin texture. So the equilibrium spin texture of the system can be computed analytically. So it's a relatively straightforward exercise. So it comprises three main terms. So the first term is a Rasch plus Spinobit coupling. So this is responsible for the winding of the spin texture. This is the familiar Rasch plus Spinobit coupling. Then the second term, it's the tilting of the spin texture out of plane, which is induced by the magnetic exchange coupling, here emphasized by the MZ symbol. But this could also be a result of Spinova coupling. And then we have the in-plane magnetic and isotropic correction that is quite complex, and this is a result of the distortion of the Fermi surface. So once the magnetization induces some in-plane magnetic exchange coupling in the system, and this is not particular of graphene or TMD, this is for any system, we have different directions in the plane, and that of course renders the Fermi surface highly anisotropic. So we have all these rich terms, but I'd like just to emphasize the last one, which is proportional to mx mz and has this harmonic dependence. So the modulus, so the strength of this term depends on where we are in the Brillouin zone around the K point, depends on the angle of the wave vector, and that will play an important role. So the out-of-plane tilting is the crucial ingredient here that activates skew scattering. And the reason is that once we have a combination of the winding, basically once we have the Rasch field and an out-of-plane tilting of the spin polarization, we have a well-quantized quantization axis for the spin. That means that electrons will skew scattering from any impurity potential, irrespective of the symmetry and type of impurity potential. So this is a quite general feature, actually happens also in standard ferromagnets, metallic ferromagnets. It's just in 2D materials, there's always something special, because what happens in a two-dimensional material is that even in the presence of time reversal symmetry, let's say we measure and switch off the magnetic exchange coupling, there will be also skew scattering all the way, and the reason is that the spin texture will also be tilted out of plane, which provides this fundamental quantization axis that activates the skew cross sections of the problem. So this will play a crucial role, as we're going to see. So this slide is possibly the most important one in the talk, or the second most important one in the talk, which explains the origin of the Spinovi torques in the system in the clean limit. So assuming that we have a weakly disordered system such that the conductivity is typically larger than 1 in units of quantum of conductance. So we start by looking at the application of an electric field along the x direction. So in blue line, you see one of the Fermi surfaces. So they're going to be typically two Fermi surfaces that counter-interact itself. So as you go towards higher energies, these two Fermi surfaces sort of merge into each other, so that annihilates any non-equilibrium effects that you are looking for. But at intermediate electronic densities and at low electronic densities, there is no mechanism for compensation. So, but it suffices to look at one of these spin textures to understand the origin of Spinovi torque, as I'm going to show now. So let's imagine now that we have the electric field applied along the x direction. So now we have the winding of the spin texture due to the Rasch effect. And we also see the distortion of the Fermi surface due to the application of the electric field. So this can be seen equally as a shift of the Fermi surface, if you prefer. So that drives a charge current that is aligned with the electric field, obviously, but that also induces a non-equilibrium spin polarization due to the spin momentum locking of the spin texture. In other words, the spins at plus and minus x directions in K space, their occupation probabilities no longer compensate each other. So whereas in equilibrium, in the absence of magnetization, they will cancel, here they will not cancel. So this effect does not even require any magnetization. It's the Rasch-Waals-Bonded effect and leads to field-like torque. Now comes the interesting part. It's when we now activate the skew scattering mechanism. So this is a way of saying, but the skew scattering will always be active in these systems. So we're going to have always interplay between longitudinal and transverse distortions of the Fermi surface. So this will induce now spin polarization that is collinear with the electric field. So that's quite remarkable and is in a sense a result of broken left-right symmetry. So now now spins spins located at plus and minus y directions in k-space no longer compensate. But this lack of compensation is because of skew scattering. So you're going to have this collinear Edelstein effect showing up. Of course, you could do the same exercise by applying the electric field along the y direction, and you're going to find exactly the same answers. The important thing to realize here is that this non-equilibrium spin polarization that is collinear to the electric field requires skew scattering, so it requires a quantization axis. So it is proportional to the mz. And this is very important because then we immediately conclude that this collinear Edelstein effect will be responsible for anti-damping torque. So if we actually now use the expression on the left and work out the torque, we easily arrive at the expression on the right. And this is the familiar Rashba type anti-damping Spinobit torque, also referred many times as M cross Y. So this is now a Fermi surface mechanism that can give rise to such a torque, and it will be a very effective mechanism in clean samples simply because the conductivity is very large. But this is not the end of the story. So now we should look at the out-of-plane component of the spin texture, which I didn't show in the previous slide, not to get confused. So now let's switch off the in-plane spin texture from the schematic, and let's just focus our attention on the out-of-plane spin texture. So you might remind from previous slide that there is this harmonic dependence of the SZ component. So the SZ component is proportional to the product of MZ and MX, and on top of that we have an harmonic dependence. And that's quite interesting. So what we need now to realize is that once we integrate over the Fermi surface to compute the non-equilibrium spin polarization density within a Boltzmann description, if you like, the spins pointing along the Z direction no longer compensate. So we have an excess spin polarization density that exists on top of the equilibrium magnetization of the interface. So this excess spin polarization density that is polarized along Z is proportional to mx and z squared, because this mechanism again relies on skew scattering, and skew scattering tau perp is proportional to mz. And finally, there is another source of out-of-plane spin polarization that does not require skew scattering at all. So this time we can look at our standard distortion of the Fermi surface that is completely longitudinal with respect to the electric field. So this grayish ring here. And you see again that by the same token, once you integrate over the Fermi surface, the out-of-planes spins no longer compensate. So we have an excess spin polarization also pointing in the positive direction for this spin texture. So the first one will give rise to anti-damping torque of type E2, which is a very generic type that is present, actually, it should be present in any interface. And the second torque is field-like and has this form. So now we like to have actual microscopic theory for making quantitative predictions about these Spinovi torques. And for that, what we can do is to look at the current induced torque efficiency as defined in this, inside this box. So this is basically the ratio of the non-equilibrium spin polarization density to the applied charge current. And using diagrammatic language, what we'll be looking at is at the spin charge bubble, which is a special case of an electron propagator. So this is the kind of Feynman diagram that we need to evaluate. And this shaded area in black represents the interactions with impurities. So this so-called vertex corrections. So there's a word of caution here regarding vertex corrections. Worded entities tell us that they are crucial. However, the popular ladder approximation may not suffice. So in particular, if we want to describe skew scattering, we have to go at least to the second, so-called second Born approximation, and that already is beyond the ladder approximation. But because we want to have a full description of Spinovi torque and to be able to capture the evolution of the Spinovi torque from weakly disordered to strong disordered potentials, we developed a full non-perturbative theory, in the sense that we can resum all Feynman diagrams that correspond to single impurity scattering events. And that give us the freedom to look at different scenarios, in particular look at interfaces with atomically sharp defects that tend to induce very strong potentials into the materials, the so-called resonance scattering limit. And another feature of the new approach we developed is that interactions in the effective Hamiltonian, and this will be a continuum Hamiltonian at this point, are treated exactly. So we can compute, in particular, all the impacts of an isotropy in the Fermi surface, and that's going to be very important. And to do this, we had to develop the composition technique, ASOT decomposition technique, that will allow us to compute bubbles in the presence of highly complex and isotropic green functions. So, and because we don't want to be too specific about the type of disorder we have in the system, because we know that spin-dependent disorder will enhance inverse spin galvanic effects and thereby also possibly enhance Spinovi torques, we want to play on the safe side here and consider just standard random scalar impurity potential. And these are the results for a typical graphene-based heterostructure with weak proximity effect. So you see the numbers below the graph. So there's a Rashba coupling of 20 millieV that is on the high side for this structure. There's an exchange coupling of 15 milli-electron volts, and there's a small in-plane component in the magnetization induced at the interface. And there's a typical impurity density of 10 to the 11 per centimeter squared. And the first thing you see in this graph is that all the responses in plane and out of plane as a function of the applied current, they tend to decrease with the Fermi energy. So this is a consequence both of the behavior of entanglement in the system that we alluded to earlier on in the talk, but also a consequence of the fact that at higher energies, we have compensation between the counteracting spin textures. But moreover, what should catch our attention in this graph is that the anti-dumping components, XX for the collinear Edelstein effect and ZX for the out-of-plane Edelstein effect, are already reasonable in the sense that the corresponding figure of merit is about 0.1%. That's quite significant in my opinion, because we are dealing here in this exercise with a simple graphene-based system with weak proximity effect. So we can also do an interesting calculation, which is to imagine that we are allowed to expand the full torque expression to first order or to zero order in this case in the angle, in the sense that these torque efficiencies TO1, TUE1, etc., do not depend on the angle. That's a typical approximation in the literature. We are doing here just for pedagogical reasons, so we can actually then compute analytical expressions in this approximation. And in particular, in the weak scattering limit, when the product of the scattering potential strength U0 and the density of states of the bare system is much more than 1, we have this very compact expression for the even torque type 1, and even torque type 2 has the same magnitude but opposite in sign. And there are several things of interest in this simple expression. First is that the anti-dumping Spinovi torque efficiency is sensitive to the scattering strength. So it grows linearly with the scattering strength. So this hints at that when we actually reach the unitary resonant scattering limits, things can get more interesting. And secondly, there's a nonlinear dependence of the torque with the Rashba-Spinobit coupling. So actually, if the exchange coupling dominates over Rashba effect, you see that this dependence is a power of 5. So it's quite fast dependence, which actually perhaps accidentally has been observed in recent experiments on bilayers with composition-dependent proximity Spinobit coupling. So this shows that interplay of Rashba effects, exchange coupling, and disorder can actually explain some of the non-trivial features seen in recent experiments. So let's go back to our favorite graphene example with weak proximity effect, but let's now crank up the disorder potential. So let's go to the actual experimental scenario of strong disorder of atomically sharp defects. So that basically means in the theory or in the calculation, we take the limit of U0 going to infinite. And when we do that, we see this striking enhancement of the skew scattering cross sections, which results in a 10-fold or even 100-fold increase in the Spinovi torque efficiency. So this depends now on the numbers, but here we are being on the safe side. And this means the figure of merit reaches, for such a simple system, 1%. Now we look into the more interesting case of a transition metal decocclusion monolayer with strong proximity effect that can be realized by taking, for example, molybdenum ditelluride in proximity to europium oxide, at least according to first principle calculations, and there's some experimental evidence that this is actually the case. So in these calculations, the exchange coupling is quite strong, can be up to 100 milliV. And the Rashba coupling also, it's remarkably strong according to the first principles calculation. So we have used those numbers and they've fixed electronic density and changed the gap of the system. So there are different, if you can think this as systems with different pressures being applied, if you like. So we changed the orbital gap and we see some variation. Please note the logarithmic scale on the vertical axis. But more importantly, what we see is that as the magnetization angle is tilted in plane, and this will be important, of course, because typical ferromagnets will have in plane magnetic anisotropy, we see now that the XX and YY components that previously were just the same. That's why in this graph I was not showing the YY anti-damping response because it falls over the XX line. Here they get separated. So you get this separation of XX and YY anti-damping response when you increase the in-plane magnetic change coupling component as experienced by the 2D Dirac fermions. So that's a very important result. Another thing that we can see from this graph is the enhancement of the ZX out-of-plane Spinovi torque efficiency. Because our approach is non-perturbative, we can actually afford to compute the full Spinovi torque angle dependence. So we can track the angle dependence of all the components of the K tensor, from which then we can construct the actual torques and torques efficiency. And this is quite interesting and shows that clearly any approximations that take these functions to be constant or just to first order in the magnetization cannot be correct. So now I'd like to say a few words about state of the art to finalize this section. So about recent experiments. First, so there's been demonstrated Spinovi-driven switching of van-der-Waals ferromagnets, not monolayer limit yet, but experimentalists are getting closer and closer. There's also some experiments with 2D materials as a source of Spinovi torque, which was the main topic of this talk today. And I'd like to highlight here the work of McNeil and co-workers, in which they demonstrated very strong Spinovi torque down to the monolayer. Unfortunately, our theory, strictly speaking, does not apply to this system because this is a low symmetry transition methodic chalcogenide, so the point group is not symmetry-free, unfortunately. So, of course, we cannot be certain about what this would be the Fermi surface contributions for this heterostructure. They would certainly play a role, but of course, there's the question of what actual microscopic mechanisms would explain the intriguing results of this experiment, in which in particular it's observed an out-of-plane anti-damping torque, M cross Z. So that's quite interesting. And there's also this wonderful idea in the field, this vision of some theorist colleagues, in particular Branislav and Nikolic, in which basically the idea is to integrate now all these 2D materials and having a 2D material not only exerting a Spinovi torque, but also a 2D ferromagnet. So this would allow us to devise new 2D Spinovi torque devices, according to our colleagues. So finally, I'd like to discuss very, very briefly just some consequences of these results for other materials. So the first conclusion is that field-like and anti-damping Spinovi torque from the Fermi surface have fundamental distinct origins in terms of scattering mechanisms. So whereas the anti-damping-like results from spin charge correlations, in other words, from spinovic scattering, and therefore they require T-matrix level vertex correction, or at the bare minimum a distorted waveborne approximation, the field-like torque efficiency is controlled by the Fermi surface topology and the spin texture. So it can be captured to leading order already by standard ladder approximation and partially by I-eta-Green's functions phenomenological approaches. That's quite interesting, and our work kind of sheds new light into this aspect. So now you may be wondering what is the ellipses inside these square brackets. I'll explain very briefly. So these are the next order terms in the virial expansion or in the impurity density expansion that we do diagrammatically. So the advantage of the diagrammatic approach is that we can separate very clearly intrinsic and extrinsic effects, and we can classify all these diagrams according to the power in the impurity density expansion. So this second term appearing there is not dependent on the conductivity in the sense that the tau dependence in the denominator cancels the tau dependence in the current J. So this leads to a torque that is very insensitive to the transport time. So this has origin in quantum corrections, side jumps and weak localization that unfortunately has not been so much studied in the literature, but I'm hoping that We can come back to this soon. And there's also a very important contribution from the Fermi C, which is the intrinsic contribution. So this intrinsic contribution by construction is very robust and does not depend on vertex corrections almost at all, at least the leading order in the diagrammatic expansion. And of course, they lead also to a torque that is independent on torque. But the basic message today is that the take-home message is that in the clean limits, so if the conductivity of the 2D interface sufficiently substantial, let's say, then the field-like and anti-damping-like torques will be dominated by Fermi surface processes, and the skew scattering will be the responsible for the anti-damping torque. So as an example, and to finalize this talk, I'll just very briefly mention a toy model of a TI surface state that's been investigated in the literature. Of course, a real surface of a TI ferromagnet is way more complicated than this toy model, but this already is sufficiently rich to give us an indication of what we are looking at. So if we take the typical ingredients and perform again the same calculation at, non-perturbatively, first we find that the field-like torque is strong, and this is not surprising. That's just the result of the spin momentum locking of the Edelstein effect. And that's the first term in the expression of the torque here in blue. So, so that's the main contribution, the main field-like contribution. And quite interestingly, the graph on the right-hand side, which now shows the anti-damping torque efficiencies, tau E1 phi and tau E2 phi, one sees that the even 2 type is much stronger. And this is a result actually of the unitary limit that has been taken in this calculation. So when the scattering potential of an impurity is sufficiently strong, according to this model, the even 1 type standard anti-damping contribution is suppressed. So that's quite interesting. And then the physics is now dominated by this other term. And now just to summarize the conclusions of this talk, Spinovi torques induced by 2D materials reflect either pseudo-spin entanglement that cannot be directly accessed experimentally, but lead to nonequilibrium effects that can be detected. And I presented 2 such new effects, semi-classical effects, the collinear Edelstein effect, that is a semi-classical variation of the topological magnetic electric effect in topological insulators, and the semi-classical out-of-plane inverse spin galvanic effect. And I also propose Spinovi torque as the main mechanism for Fermi surface contribution in sufficiently clean samples, and this also sheds new light into recent results for ballistic nanoscale devices. And finally, as a conclusion here for theorists in the audience, a full-fledged diagrammatic approach is absolutely essential to capture the strong scattering regime, but also to capture the angular dependence in the diffusive samples, even for weak scatters. And with this, I finish. Thank you very much for your attention.
Thank you very much, Iris, for this interesting talk. So we are now ready for questions. If you are in Zoom, just use the raise hand feature. If you're watching on Twitch, just type your question into the chat box and I'll read it. You may need to register for an account with Twitch if you want to do that. So Alexei Kolev, please go ahead with your question.
Hi. So I did not understand the connection between entanglement and spin-orbit torque. So spin-orbit torque is a single particle, is described by single particle theory, while for entanglement you need 2 particles. So what is then the, could you like explain better what is the connection between spin-orbit torque and entanglement?
Sure, thank you for this question. My apologies. I've been through this concept very quickly, so hence the confusion. So let me just go back maybe to the slide that could help. Just a second. Sorry, yeah, here it is. So I absolutely agree. So the Spinovi torque is single particle. It can be explained within a single particle description, but one should have in mind that the entanglement calculation that, or the entanglement described here, is the entanglement between 2 internal degrees of freedoms of a quasi-particle. So this is, again, a single particle description. So I'm not looking at entanglement between 2 quasi-particles. I'm looking at entanglement between internal degrees of freedom within the same quasi-particle. So this is within a single particle description. So all the talk was based on a single particle description. So Fermi-liquid description, if you like, for quasi-particles. So now, as for the relation to the Spinovi torque, that's a very good point. So this is just an intuitive approach. There is no rigorous results that I know relating the entanglement of the internal degrees of freedom of 2D materials to Spinovi torque capacity. This is just an intuition that we know from the literature, that the Edelstein effect, that is a very fundamental effect that will always take place in interfaces of broken inversion symmetry. We know that spin and orbital degrees of freedom are maximally entangled. So we have a sort of a singlet. And so you'd expect that this correlation will help ending up with large current induced Spinovi torque. And we saw a correlation between these two things. So basically, systems with higher degrees of entanglement in this sense end up having larger current induced Spinovi torque capacity. Of course, this is not a one-to-one mapping, so that's why I was careful to say that this is an intuition here. So, but thank you very much for the question. That's a very good point. Thank you.
Thank you.
Okay, thank you. Jairo, if you want to go with your next question.
Yeah. Thank you for, sorry, I caught only half of the talk, unfortunately, but so I have a few comments, some puzzling statements that you may have made, but maybe I just missed the beginning of it. So clearly, of course, we know from our experience with anomalous Hall effect, as actually the previous questionnaire, Alexi knows very well, that this idea of these vertex corrections can disentangle this notion of the side jump, the intrinsic contribution, and the skew scattering contribution. But we also know fairly well from the data, at least in anomalous Hall effect, which is fairly unambiguous, that any skew scattering contribution really is not dominant at all in anything that other than extreme conductivities. This is evidenced by many, by the data that we showed in the review of modern physics, and the data that is evidenced also often in many of the Spinobi torques cases, experiments. There's not many that actually show systematically this dependence on tau. But this notion that as tau goes to infinity, of course, we know this theoretically, but it doesn't happen practically, right? Do you have any connection to the experiments that justifies these statements that you made that they will dominate at all experiments themselves?
Thank you for the point and for the question. So, when I say they dominate, what I meant is they dominate in the diagrammatic expansion. So in the clean limit.
Aries, I mean, we understand what an expansion is. We have a small parameter. We understand that it will go to infinity, but at the end of the day, there is a prefactor there that is important to match the experiment.
Yes, we have good evidence that
to actually connect to experiment. This is my question.
Of course yes, of course it does. So we have good evidence in 2D material-based systems that there's evidence that in recent experiments that extrinsic effects and in particular skew scattering could play a role. So I mentioned in the beginning of my talk, maybe you haven't seen that slide, so we can go back.
So unfortunately, I missed at the beginning. So
that there are recent, very exciting recent results that you probably are aware of. So let me.
I'm not aware.
Yes. So yeah, right. So there's been recent results that show that well, they don't show directly, but we can infer by doing theoretical analysis as usual that the extrinsic contributions are important. So, but you are absolutely right that the samples, they tend to be somewhat in the so-called dirty regime. And in the dirty regime, then skew scattering may not be the most important mechanism, at least the skew scattering from a single impurity, because there are quantum interference processes that also correspond to skew scattering events that just are much more complicated to evaluate.
Yeah, remember, I did write the 2007 paper that explained that. on anomalous Hall effect.
I'm answering.
Same diagrams that you use in the other ones, yeah?
I'm just answering the question. So then these processes will kick in at the same order than the intrinsic contribution. So,
Yeah.
for example, so that means that in a typical, I mean, in a scenario that we don't know for sure what is the dominant mechanism, and for sure I don't know for 2D materials because it's a very recent research, as you know, then we need to be careful from the theoretical perspective and evaluate all these processes, all these contributions carefully. So of course, this is the first step. So this is the first microscopic theory that is non-perturbative. I think that's already a good advance that we did, so that we can capture the Spinovi torque dependence, the angle dependence, I mean, and we can capture the resonant regime. This was not done before for any system. So we actually had to develop an entire machinery for doing that. So this was the work with Mirko Militari a few years ago. We started with extrinsic Spinova effect in graphene, and recently my students generalized this to include intrinsic Spinobit coupling in the wave functions that make, of course, the problem much more complicated. So, of course, we can also use different types of machinery. Tight binding models can also help, but that's, of course, a different topic. So, but you're right. So the Skew scattering may not dominate. Yeah.
Let me follow up on a question, actually, just mostly because I haven't followed it, but I would be grateful if actually you send me some of the references later. I apologize for not having followed those papers.
No, no need to apologize at all.
No, but I still do. But this is mostly an important puzzle that I had before, but maybe something that you may have researched in the later developments. When looking at particularly 2D systems, these are very keen to be worked on in the Landau-Bodecker non-equilibrium dysfunction regime that is being exploited a lot by Branislav, for example. Mm-hmm. And in this case, often here you can actually do a mapping, obviously, of the Skew scattering and all the scattering mechanisms to contributions at the Fermi surface. They are obviously connected because they are topologically connected effectively, but there is a bit of this deep level diagrams that are still not resolved. Have you done a study at all in the 2D systems comparing the 2D by looking at essentially non-equilibrium dysfunction formalism and the cuboformalism to see if they match? Essentially, my question was because we followed it, and you may be aware, I'm not sure if you're aware of in the anomalous effect, when we were trying to disentangle this idea of a skew, side jump, and that it was a puzzle for such a long time, we chose a very simple 2D model to try to do it basically all three ways: non-equilibrium functions, semi-classical, as well as Kubo. And this is where we began to disentangle that, okay, yeah, what one used to define the skew scattering as the asymmetric contribution from it was wrong and things like that. That you have also figured that out within the context of the very important context of the torques. But I never really achieved or satisfied myself of connecting the Landau-Bodecker one correctly in a realistic system. And now with these 2D materials being there, the magnetic 2D materials, there may be a hope. Have you guys approached it that way at all or not?
That's a very interesting point. And that's a very fundamental question. We have not looked at that. So we are on the verge now of being able for the first time to extract such extrinsic contributions using cuboformal with tight binding models. That's extremely difficult because we need to do calculations in extremely large systems because the resolution and mid-level spacing has to be much below the typical self-energy induced by impurity. So that requires ridiculous large systems with comprising sometimes 10 billion orbitals when we do the math, especially in 2D, because 2D, because of the direct spectrum, the mid-level spacing goes as 1/L, not as 1/L squared as in a typical parabolic system. So it's quite difficult to do any numerics, but we successfully tackled that with respect to Kubo formula and usual regimes that we study with the Kubo formula. As for your other points on the non-equilibrium function and Landau-Bodecker, we have not done any studies on that direction. And of course, I do know about studies that have employed these techniques to look at the ballistic regime and chaotic regimes. Mm-hmm. But any connection between these two worlds will deem to be difficult, I believe. So,
but they have to be there, right? I mean, they have to be the same. They cannot be different. They're just different.
The physics is just one. I completely agree. The physics is just one, and they have to be the same. And but the connection may not be easy because they may require very large calculations.
Yeah, no, it's a difficult challenge, but I think it's an important one.
It is.
But I'm again sorry for not having followed, but we're very happy. Sorry for taking over so much. I'll stop now. Please contact me directly, and then I guess I would love to continue the conversation at some point. Thank you.
Thank you.
Okay, thank you. Are there further questions, please? Let me ask you something about the angular dependence. So there are a few different terms with different cross products that you had on your slide, and my understanding is that you classify different terms as feel-like or damping-like based on the power of the magnetization, right? So yes. Even or odd, which is not necessarily, which is not the only way to classify them. So, for example, there's a way to classify different terms in terms of vector spherical harmonics, as we suggested in a recent paper. I'm not sure if you're familiar with that. But the advantage of that expansion is that different terms are orthogonal, and each term is either purely dissipative or purely non-dissipative, in the sense that it would contribute to the damping in an FMR experiment, for example, like the curl of the effective field on the sphere vanishes in some terms and in some terms not. So it may be reasonable to define feel-like terms as those that are not dissipative, and damping-like those that look like damping for a small angular precession. And in that description, so the term that you call E2, I believe, this M cross Z MX, it is actually a linear combination of a simple feel-like term, right? So this TE2, no, sorry, TO2, yeah, TO2. Okay. So this TO2, if you expand it in vector spherical harmonics, you get one piece that looks like TO1, so it's not orthogonal to TO1, and that's a feel-like term. And then there's another term that is damping-like in the sense that it does affect damping. So I wonder if this property of being feel-like in this sense is somehow connected to the microscopic mechanisms and the contributions from different kinds of diagrams. Do you have any comments on this?
Thank you for these interesting points. So yes, I'm aware of your work, so quite interesting. So let me just first say that that you're absolutely right for the purpose of this talk, and also this was the convention used in our paper for simplicity. We have named these torques according to the powers. But as you said, this situation, the full torque is way more complicated, and that's what we show here precisely, because all those T1, etc., they depend on the angle. So they actually can expand them. It's an infinite expansion in the magnetization. Of course, you can reorganize this series in different ways. As to the connection to the microscopic mechanisms, so let me go back go back to the slide. Just a second. I will have some extra slides, but I don't have that information here. But let me grab. Here it is. This one. So So what clearly comes out of this study, and again, as Yasinova mentioned, we focused on the leading contribution in the imperial density expansion, so to the terms that are proportional to tau. So in other words, these efficiencies here do not depend on tau because the tau dependence will be in the current, inside the current. So in this case, inside this vector Pj. What we learned from this study is that these dominant dependence, which comes fundamentally from the spin charge, from the three-leg correlation function, which can be classified according to the symmetries in mx and mz. So this three-leg correlation function, the K tensor, it has can distinguish in terms of being odd or even in these parameters, in the magnetization parameters mx and mz, or mx, mz, and my in general. And what we could observe is that terms that lead to even dependencies in the torque, like the one shown here, they are dominated by skew scattering. In other words, if skew scattering is absent from the calculation, so if we perform a standard ladder correction, vertex correction, these terms will be exactly zero. So we can still perform a diagrammatic calculation, but this diagrammatic calculation will give an inconsistent result that is proportional to tau. So we're going to have a tau square dependence overall. So this was the key observation that we made in our study, is that the anti-damping terms, in the sense of terms that come from even powers, they are strongly normalized by vertex corrections, by skew scattering, whereas the field-like terms, so to say, they are mostly controlled by the Fermi surface topology and spin texture. And but this aspect, I think, was already very clear in the literature, that we could very well describe these odd components of the torque and the magnetization using the standard ladder approximation. So this does not require a complete understanding of the hierarchy of transport times that dominate the steady state of the problem, because even though I've mentioned tau perp and tau parallel, in fact, for a two-dimensional typical material, there are 64 microscopic transport times. And so it's quite complex. But the point is that for the field-like terms, so the odd terms in the magnetization, what we found is that the basic tau parallel is the contribution description, the relaxation time description, if you like, within Boltzmann, suffices to get a very good approximation. So that is the connection we did between the microscopic origin of these effects and then the symmetry classification of the torques in terms of powers of magnetization. So we didn't went that far to actually try a different writing of the series with spherical harmonics or any series of orthogonal polynomials of our preference, but of course that can be done because we can evaluate to numerical precision the Spinovi torque for any angle.
Yes. Yeah. Thank you.
Thank you.
Okay. Does anyone else have a question? I don't see questions on Twitch. So if no further questions, let's thank Iris. You can use the clap button under the reactions in Zoom.